Hello, and in this video I'm going to cover section 10.7, Volume and Surface Area from Contemporary Mathematics by OpenStax. The learning objectives for this section include calculate the surface area of a right prism and cylinder, calculate the volume of right prisms and cylinders, and solve application problems involving surface area and volume. So in geometry, three-dimensional objects are called geometric solids. So that's a nice vocabulary word. Surface area refers to the flat surfaces that surround the solid and is measured in square units. So that's like the sides of the object. And then volume refers to the space that's inside the solid. This is measured in cubic units. So to go back to what we've previously discussed in the metric system section, remember area, including surface area, is in square units. It's in square units. So for example, meters squared, inches squared, centimeters squared, so forth and so on. Right, and then volume, and that's, sorry, let me back up for a sec, and that's because area of like a basic rectangle or something is length times width. And so if you think of it like that, you got a length of meters times a width of meters, then you get meters squared. And in most of those polynomials that we talk about, you're usually only multiplying two types of linear units together. So even, for example, the area of a polygon, which is 1/2 a times p, you still get 1/2, which has no units, a, which is the apothem, so that's 1/2 of, we'll say, for example, x meters, or I'll say inches since that's the US system, and then p would be the perimeter, that would be y inches, and so that's just 1/2 x times y, and then inches times inches is inches squared. So you still get those square units from area of a regular polygon. In the case of volume, and I'm sure there's a picture on the next slide, but I just want to talk about it here because this is where it's, mentioned, is for things like a rectangular prism, you have length, you have width, and you have height. So you've got 3, length times width times height for the volume. So again, going back to that, if we did like x, we'll do m for meters, and then y meters, and then z meters, then the volume is going to be x times y times z meters cubed, because there were 3 of them. So it's cubic units for volume. All right, so we've got some more vocabulary terms here. A right prism is a three-dimensional object that has a regular polygon-shaped base and a congruent regular polygon-shaped top, and the lateral sides are parallelograms. In a right prism, the lateral sides form a 90 degree with the top of the base. So for example, let's see if I can draw a pentagon. Right, there's a pentagon. And so all they're saying here is coming out of the lateral base, we would have, for example, something like this, and then on the back side, we wouldn't be able to see it, but it would have kind of, oops. Let me do it this way. So this would connect to there, because that's on the outside. And so back there, that would all be kind of hidden from us. And so if we were to kind of look at this face here that I've colored in gray, that's congruent to this face in the back. So those two pentagon faces, pentagon faces are the same. They are congruent. And then each of these sides, which I will color in a light blue. So these sides here, they're parallelograms in that this side is parallel to this side. And so we create this three-dimensional sort of volumetric shape. So there is a formula, a generic formula for, in this case, the surface area. So we do have a generic formula for the surface area of a right prism. It's equal to twice the area of the base plus the perimeter of the base times the height. So that's, given by this formula here. And so it's 2 times big B, where big B is the area of the base. And so that's going to change depending on what your base figure is. And then the pH is the perimeter. I will get my pointer here. Is the perimeter around the sides, times the height. And I'll talk about this a little more and explain kind of how you could do this without this generic formula. But the volume is also nice because the volume is, and I think this might be a typo from the textbook. This, I would say, is V. So the volume is big B. Again, that's the base of the face. In this case, this example I gave was the pentagon, times the height. And so that's kind of where the volume comes from. Now, I like to describe this volume formula kind of like bread. So imagine you had, I'm just going to draw a rectangular prism because that's easier. So let's say you had, a rectangular prism. So here's a rectangle, and let's go out. Okay. Now, let's say this was a loaf of bread. So this was some bread here, and you baked a perfectly rectangular prism's loaf of bread, and you took a slice of that bread right here. Right. Let's say you took that slice of bread and you brought that out. So let's bring that slice of bread right here. And let's say it was so thin that, it's, in math, we could say that it's infinitely thin. So it's literally just this one slice of bread. Then the area of this little slice of bread, if this is the length and this is the height, right? This is the length and the height. Then the area of that little slice is going to be length times height. Or, in this case, that's what it looks like. So it's length times height. And then, so that would really just be the area of one of these faces, right? That's just the area of this face or this unseen face in the back. So this unseen face in the back, this congruent face in the back, which also has height and the same height and length. And then what you've done is you've taken a slice and you have W of them, right? Because the whole width of this is W. So if you have one face is length times height, and then you have W of them, so you multiply it by W, that gives you length times height times width, which we usually just say is length times width times height, right? And so that's where the formula for volume of a rectangular prism comes from. But if you had, for example, that pentagon, see if I can draw it. And so in the back there, we've got this unseen side, right, that's connecting there. We've got that unseen side. Then our slices of this particular bread would look like a pentagon. And so we would have to consider, well, what's the area of this face, right? Well, that would be 1/2, and then we have to know, you either have to know the area or use like the apothem or something like that in order to find it. But we would have this area, which we'll call big B. So the volume in this case would be big B times, well, how many slices of this do we have? Well, it depends on how wide or how tall, in this case, depending on what you want to say, they call it the height. So how high it is, if you stood it up on its face, it would, be like a tower. And so that's big B, which is the area of the face, the base face, times the height. And that's where those two formulas come from. That's where the volume formula comes from. The surface area I'll have to explain on a separate page. Let me bring up, here's just a piece, blank page. So let's look at that. So here, let's go back to that pentagonal prism. And so we're looking at surface area here. So surface area. So first, it's kind of this area that we've colored in, right? And remember, we've got another congruent one back here. So there's two of them. So this is, again, big B. This is also big B for area of the base. So if we're talking about surface area, we've got two copies of big B. If we're trying, I like to think about this as painting. So if we're trying to paint these two, if we're trying to paint these two faces, oh my goodness. I keep erasing when I don't mean to. There we go. So we're trying to paint these two faces here. We've got two copies of it, so that's 2B. Now, these sides, let's say we wanted to calculate the area of this side here, right? So if we wanted to calculate the area of this side, we would need to know, like, what's the length of this side, right? And that's going to be whatever the length of the side of the pentagon is. That's going to be the same length as here. And then if we call this the height, because that's how quote-unquote tall the figure is, then one of these figures is, one of these sides is going to have area length times height. But in the case of this pentagon, we have 5 copies of it because it's got 5 sides. So there's one down here on the bottom that you can't see. You've got this side that we've highlighted. You've got one over here and another one. So you've got 5 copies of that. So another way we can keep up with that is the perimeter, right? So this would have 5L times H, right? And so that L times H gives me the area of the lateral sides, and that 5 from the perimeter helps keep up with how many sides that is. So that's going to be plus the perimeter times the height. And that's where that second formula, when we talk about on that last page, well, technically it was the first formula for the surface area, comes from. So here's a formal definition of a right prism. This is what I've been trying to draw. It's just like this is a little better. You can see here we have this face here. This is the top face. This is the pentagonal face that we have here. That's the same down here. This is also a pentagonal face. It's got the 5 sides. Those are congruent. They are the same shape, top and bottom. And then we have these lateral sides here, and there's 5 copies of them, and they're all the same, right? And so I'm just going to color in these visible ones here. And so that kind of gives you an idea and a look at what we're talking about. So if we were talking about surface area, right, we've got this big B and big B here, so that's 2 copies of big B. And then we've got these 5 sides, L, 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 right? They all have length, so there's 5 of those times W, times height. We'll call this the height, times height, but 5 times L is the perimeter again, so that's 2B plus 5PH, which again gives us that, because 5L is P, gives us that kind of help keeping up with the areas of the lateral sides. So let's do an example. Let's find the surface area and volume of a rectangular prism. These are probably some of the easiest to do. So let's start with the surface area. So we've got big B here, and we've got another copy of big B there. So big B is going to be 5 centimeters times 3 centimeters. So that's going to be 15 centimeters squared. So 2 big B, I'm going to write the formula, plus perimeter times height. So that's going to be 2 times 15 centimeters squared. Now, the perimeter is of big B. So in this case, this top up here will also be 5 centimeters, and this side will be 3 centimeters. So we're looking at 16 total centimeters. So that's the perimeter. So perimeter is 16 centimeters. And then the height is given by, it doesn't, I know it says W, but you can think of it as the height as 10 centimeters, so 10 centimeters. And so that's going to be 30 centimeters squared plus 160 centimeters squared. So we're looking at 190 centimeters squared. All right, so let's say that maybe that was a little involved. Maybe you thought, I don't really understand the perimeter connection. Well, then take a step back and just look at what the different figures are. So start with big B here. There's 2 of those, and we know that that's 3 times 5, so that's 15 centimeters squared. So there you've got 30 centimeters squared. Now look at this side here. Let me highlight it in blue. So look at this side here. Right? That is 10 by 3, right? So we'll call this, we'll call it side 1. So side 1, there's going to be 2 of them because there's another side 1 over on the other side that's going into the paper, or into the screen in this case. And that's also going to be 10 times 3. So we'll have 2 copies of 10 centimeters times 3 centimeters. So I'm just going to call that 30 centimeters squared. So that's 60 centimeters squared. And then finally, on the top, we've got another rectangle here. And so we'll call that side 2. So side 2, there's going to be 2 of those. There's one up top, and then there's another S2 on the bottom that we can't see because it's sitting flat. So that's going to be 2 times. Now it's going to have this length of 5, and this length here, try to bold it in, is going to be 10 centimeters. So we'll have 10 times 5, which is 50 centimeters squared. So that's 100 centimeters squared. And so if you paint each of those sides individually, all you have to do is add these up. 30 and 60 make 90, and then 100. You still get 190 square centimeters. So it doesn't matter which formula you work with for the surface area. If you understand breaking it apart better, awesome. If you like this formula because it, just kind of makes sense, that's great too. It really just depends on which one makes sense and which one, is more efficient. Sometimes it's gonna, the perimeter version is gonna be the only one you can use because of the information that you're given. All right, so then finally, let's do volume. There's really only one way to slice the volume, and that's length times width times height. And so that's going to be 5 centimeters times 3 centimeters times 10 centimeters. And so that's 5 times 3 is 15 times 10. So that's going to be 150 cubic centimeters. And that's it. So our volume is 150 centimeters and our surface area is 90 centimeters. 190 centimeters, sorry. Squared. All right, so let's look at finding the surface area of this triangular prism. All right, so again, there's kind of 2 ways you could do this. I'm going to start over here on the right and see if we can use that perimeter formula. So I'm going to highlight some things here. So if this is 12, remember these are congruent triangles. So that means this up here is also 12 inches. And so if this is 10, that means this is also 10 inches. So when we're going to find the surface area, it's 2 times big B plus perimeter times height. Now again, they've chosen this to be W. I'm just going to call it H because that's going to be the height for me, or you could call it width. It doesn't really matter what you call it, just as long as you use it correctly. So big B in this particular problem is the triangular face. This is a isosceles triangle because two sides are the same. So in this case, the perimeter of big B, oh wait, sorry. We want to find the area of big B. So big B is going to be 1/2 base times height. Now this is talking about the triangle. So it's 1/2 the base of the triangle, which is that 12 inches, times the height, which goes down the center, in this case is 6 inches. And so that's going to be 1/2 of 12 is 6 times 6, so this is going to be 36 inches squared. So big B is 2 times 36 inches squared plus. Now we've got the perimeter. So the perimeter in this case is going to be 8.49 plus 8.49 plus 12. And that perimeter is going to give us, so perimeter, I'll write that right here, that's 28.98 inches. And then the height is, again, the height of this prism, which is 10 inches. So that's going to be 2 times 36. So that's going to be 72 inches squared plus. And then 28.98 times 10 is 289.8 inches squared. And so if we add those together, I'll do that in the calculator. That gives me 361.8 inches squared. And so that's going to be the surface area. I kind of think of it, that's how much paint I'm going to need. And I know it's odd to think about it, but paint is measured in square inches because it covers surface. 36.8 inches squared. Now, you may be thinking, okay, that's a lot to keep up with. How do I break that down? Okay, well, I'm going to come over here and I'm going to erase this picture. We're going to do this completely again. So if you understood that, you can skip, a few minutes ahead and not have to watch this explanation again, because we're going to get the same answer. But if that didn't make a lot of sense, if that was, that just didn't click with you, because it's okay, it might not. Maybe this does. So we're going to break this up into the different shapes. So the first two shapes that we are guaranteed to have are the two triangles, because there's another triangle down here in the bottom that we can't see that's the same. It's 12 inches at the base and 6 inches tall. So that's our big B. So that's going to be 2 times, there's 2 of them, and the area of that triangle is 1/2 the base, and the base is 12 inches, times the height, which is 6 inches. So that's just going to be, 2 times 1/2 cancels, or it's just 1. And then 12 times 6 is 12 times. Since I'm on camera, I just want to make sure that's 72 square inches. Okay, now that takes care of the 2 bases. What are the other figures? Well, another figure is this rectangular face here. It is height of 10 and 6 inches wide, right? So that's this face right here. Now there's only one of those because it's a 12 by, sorry, it's not 6, it's 12. It's down here. So 12 by 10. There's only one of those, so we'll call this side 1. So here's side 1. So it is 12 inches by 10 inches, so it's 120 square inches. And then the other sides are over here. You just can't see them because they're going into the screen, and they are the same actually. They're little rectangles. I'll draw them right here that have a length of 8.49. So 8.49 on one side, and it is 10 inches tall on the other. There are two of those because it's an isosceles triangle. They're the same. If it was a scalene triangle, we would have 3 separate rectangles, but since it's isosceles, these two are the same. So we can call this S2, and we'll have 2 copies of those. That's 8.49 inches. There's 2 of them, so 2 times 8.49 times 10 inches. And so that's going to be 84.9 times 2, and that's going to give me 169.8 square inches. And so if I add all those together, my total surface area is going to be 72 plus 120 plus 169.8. And that does in fact give us 361.8 square inches. So I know you're like, well, you just got the same answer. Well, yeah, I'm just trying to show you that you can break it down into its faces, or you can think of it from the terms of this perimeter method. They get you the same answer. It's just what makes sense to you mathematically that's correct. So another interesting figure that's kind of special is right cylinders. You can think of these as your like soda cans. So right cylinders have circles as bases. So they have circles as bases. My example when I'm teaching this in front of students is I like to think about the little inside of a toilet paper roll, or a toilet paper, or rolls of toilet paper in general, because if you take that roll of toilet paper, you take that roll of toilet paper, right, and you were to cut it right down the middle, how does it unravel? Well, it unravels into little squares, right? That's the selling point of toilet paper, is how many, sheets, how many squares of toilet paper are there. So cylinder is really just a rectangle that's been rolled around, and the base is 90 degrees going up. And so we can calculate surface area and volume. They just might not make as sense. Volume's going to hopefully make perfect sense, because imagine you could, bake a perfectly cylindrical loaf of bread. Then every little slice of bread is going to be a circle, which we know the area is equal to pi r squared. And then how many of those circular pieces of bread do you have? Well, you would have however tall the bread is. So the volume, if you added all those slices up, would be pi r squared times the height. So that's where the volume formula comes from. The surface area one is the weird part. So if you were going to paint this cylinder, you'd have to paint the top. And then, of course, there's that hidden bottom piece. So this is, again, like big B. And so you've got this bottom piece down here that you'd also have to paint. But along the outside, remember this goes all the way around, like it circles around itself when we're painting it. But it's unraveled into this rectangle, right? And so how much area is on the rectangle? Well, it's this length up here times the height of the rectangle, right? So for surface area, we've got the two circles, so 2 pi r squared should make sense. That's the two big B's, plus the area of this rectangle that's going on. And so we've got this side here. How long is this side? Well, the length of that side is how round the base is. Well, the outside of the base is called the circumference, right? And that's 2 pi times the radius. And so this length up here is 2 pi times the radius. And so that's going to be 2 pi r for the length of it, if we were to unravel that toilet paper roll, times the height, because that's how tall the toilet paper roll would be. And that's how we get the surface area of a cylinder. And that's the two formulas. That's the surface area and the volume for cylinders. So let's look at an example, and I like what they've done here. You can see it's like paper towels. They've kind of unrolled it and shown you that it makes this rectangle. This is going to be 12 inches. And then one of these is going to be, well, no, it's not 5 inches. It's going to be the circumference here. So first let's find the surface area. So the surface area is 2 pi r squared plus 2 pi r times h. In this case, it's really just easy to remember that, but you can dissect it. We've got the two circles here. So that's going to be 2 pi times 5 inches squared. That's going to take care of the two big B's. And then the rectangle, from unraveling it, that's going to be 2 pi times the radius, which is 5 inches, times the height, which is 12 inches. And so what we get here is 50 pi square inches plus, let's see, 5 times 12 is 60, times 2 is 120 pi square inches. So we're looking at 170 pi square inches. And so if I just get to two decimal places, 170 times 3.14159, that gives me 534.07 square inches. So that would be the surface area. For the volume, it's just pi r squared times the height. So pi times 5 inches squared times 12 inches. And so that's going to be 25 times 12. So 25 times 12. That's 300 pi. Now this time it's inches cubed because you had square inches times an inch. So you've got inches cubed plus volume is in cubic inches. And so 300 times 3.14159 is 942 we'll go 0.5. We'll just go to one decimal place. So 942.5 cubic inches in that case of volume. So you got a lot more to fill it than you do to have to paint it, which in most cases makes sense. All right, so that's all that I have for section 10.7 for this video. There's a lot more examples and importantly, those your turn problems in the textbook. So if you haven't done so already, head on over to the textbook, read section 10.7 as you're going through, taking some handwritten notes. Try those your turn problems. The answer to those are at the end of the section. That checks your understanding to make sure that you know what you're doing. And then once you're done with those, head on over to the learning management system and work on your online homework to reinforce what you've learned.